Now it might seem like it would be complicated to work with buffers mathematically and figure out the pH of a buffer solution. What's the mathematical impact of the common ion effect, etc. But we'll do a quick derivation here that's going to lead us ultimately to what we call the Henderson-Hasselbalch equation. And once we've done that derivation, you can just use the Henderson-Hasselbalch equation from there. So if I have a conjugate acid-base pair, I could say the acid plus water is going to be in equilibrium with the base plus H3O plus. And actually, I'll use the same notation that your textbook does. So HA, oops, and this is A minus. So these are a conjugate pair. And if I take a nice table and I'll have some initial concentration of the conjugate acid, and I'll have some initial concentration of the conjugate base, because remember, buffers contain both of these in solution, and we've got 0 H3O plus. Now I could do an ice table minus x plus x plus x, and here I get x, and I get a minus not minus, oops, that's a plus x, and I get HA not minus x. There we go. And so I know that KW, not KW, sorry, Ka, the acid dissociation constant, that's going to equal x times A minus not minus x over HA not, hold up, sorry, again, that should be a plus. I'm getting sloppy here, sorry. So A minus not plus x, that's the initial base concentration plus x, and then HA naught, this one is a minus x. And now we're used to doing ice tables, and what do we do at this point? We hope that we can assume that x is small in both of these cases. And when you consider that you have the common ion effect in place, then that's a particularly good assumption. You know, if the Ka is 10 to the negative fifth or smaller, then we usually are pretty comfortable ignoring x, even if you just have zero amount of the conjugate base present. Well, you add some conjugate base and the common ion effect, and it becomes even easier to justify ignoring the value of x. So Ka is going to equal now x times the concentration of A minus naught over the concentration of HA naught. And what is x at this point? It only, if we end up erasing it from here and here, x is just your H3O plus concentration. So let's rewrite the whole equation. Actually, I want more space here. So I'm just going to erase this. We've already taken from the ice table everything we need. We know that Ka is equal to x, which is just the H3O plus concentration, times the initial A minus concentration over the initial HA. Well, now we're almost there. We're really close to the Henderson-Hasselbalch equation. From here, we'll just do a bit of algebra. Let's say that the H3O plus we want to be alone on its own side. H3O plus then is going to equal Ka plus, oh, no it's not, it's going to be minus, there we go, times HA naught over A minus naught. There we are. Sorry, I was getting ahead of myself, and I had to make sure this was going to work out in the end. All right. Well, how can we use this? If I want to convert that H3O plus into a pH, I would take the negative log, right? So I'll take the negative log of this, and if I take the negative log of that, I need to take the negative log of everything over here. And so that's going to give us the pH on the left side. And then let's recognize that if I have the log of the product of two different numbers, I can turn that into the sum of the logs of each of the numbers. In other words, the log of A times B is equal to the log of A plus the log of B. Does that make sense? And so we can split this up into the negative log of Ka. Guess what? That is the pKa plus the negative log of HA over A minus. And then finally, one more simplification is that the negative log of, let's say, A over B is equal to the positive log of B over A. This sign change can become a -1 exponent for the argument inside the log. We got pKa plus the log of the A minus naught concentration over the HA naught concentration. And this here finally is the Henderson-Hasselbalch equation. If you didn't follow every step of that derivation, that's fine. I just want to point out that like so much of our treatment with ICE tables, this equation depends on the assumption that X is small in the ICE table. And so the Henderson-Hasselbalch equation isn't perfect. It only works under those conditions where X is small. But for buffers, that condition is great, and this is our equation to find the pH of a buffer. Okay, so this is the Henderson-Hasselbalch equation. Let's actually just write it up top. I'll rewrite it because we'll be using it for the rest of this section. So pH is equal to pKa plus the log of the concentration of A minus. And we'll put an initial there. That's the initial concentration of the base over the initial amount of the acid in a conjugate base pair. Okay, so if I have this ratio, A minus over HA, if I have this ratio less than or equal to 10 and greater than or equal to 1/10, then that will represent a pH range of pKa. I'll say the pH is equal to the pKa plus 1 and minus 1 on either side. So if I have 10 times more conjugate base than I have conjugate acid, well, the log of 10 is 1, and so the pH is equal to the pKa plus 1. And if I have 10 times more acid than base, then we would have the log of 1/10, which is -1, and the pH would equal to pKa minus 1. And this represents the range over which a buffer is effective at resisting changes in the pH. In other words, this represents the range of the buffer capacity. Okay, so we can see that as you, let me actually refer back to that figure 17.1, where you add acid or you add base and the amounts of your conjugate acid-base pair were kind of shifting, right? If those numbers stay within this range, if the ratio of base over acid stays within this range, then the pH is going to change by only plus or minus 1 pH unit, which is pretty small, all things considered. But pretty rapidly beyond these ranges, the Henderson-Hasselbalch equation's assumption that x is small begins to fail. In particular, you can easily get to the point where you should have a zero amount of your base left if you add enough acid, or zero amount of your conjugate acid if you add enough base. And those will blow up mathematically for one reason or the other. The log of 0 is problematic, and having 0 in the denominator is problematic for your calculator. So things start to fall apart as far as the Henderson-Hasselbalch equation outside of the buffer capacity, and things start to fall apart as far as chemistry and changes to the actual observable pH of a system once your ratios get out of this buffer capacity range. So what that means is that if you want a buffer to withstand changes in pH, then it's not enough just to have some conjugate acid and conjugate base present. And it's not even enough to have them in the right ratio. But the stronger, more resilient you want your buffer to be, the higher you want these concentrations to be. You know, if I have 5 millimolar here and 5 millimolar there, then I'll get a pH equal to the pKa. But only 5 millimoles per liter would be enough to break this buffer. If I have 5 molar in A minus and 5 molar in HA, then my pH will still equal the pKa, but now it will be able to withstand almost 5 moles per liter of acid or base being added before the buffer capacity is broken. So the pH of a particular solution depends only on the ratio, but the buffer capacity for higher concentration buffers is going to be larger than the buffer capacity for dilute buffers. Okay, I think this is enough theory. Let's put it into practice. Okay, so H2S is an acid with a Ka equal to 9.1 times 10 to the negative 8. And we want to find the pH of a solution if 2.7 grams of H2S are added to 1.5 grams of NaHS in a total of half a liter of water. Okay, so we have 2.7 grams of H2S, 1.5 grams of NaHS. We put them in 0.5 liters of water. How can we find the pH? Well, we are going to have to find the concentration of the base. That would come from our 1.5 grams of the sodium hydrogen sulfide. And to find the concentration of the conjugate acid, that would come from the 2.7 grams of the hydrosulfuric acid. So in order to do that, we're going to pull up a console here. Oh, actually, you would first need to find the molar masses of H2S and NaHS, which I already have here on my notes, but you would just want to calculate them. And so let's figure out what's my concentration of acid. 2.7 grams of H2S, and I have 34.1 grams of H2S is 1 mole of H2S. And we're going to divide that by 0.500 liters. And now we'll go to the calculator. So we have 2.7 times, 2.7 divided by 34.1 divided by 0.5. That's a 0.158 molar. 0.158 molar. Okay, and let's figure out the concentration of the conjugate base. 1.5 grams of sodium hydrogen sulfide. Sodium hydrogen sulfide has a molar mass of 56.06 grams for 1 mole. And we'll divide that also by 0.500 liters to figure out the molar concentration of the conjugate base. So 1.5 divided by 56.06 divided by 0.5. Now this is going to be only 0.0535 molar. 0.0535 molar. And then let's figure out what the pKa is. The pKa is going to be the negative log of the Ka. Let's just figure that out real quick. Negative base 10 log of 9.1 E negative 8. And that's a 7.04. We should only get 2 sig figs for our final answer, but because this is kind of an intermediate, let's go ahead and carry an extra sig fig there. 7.041. 7.041. Okay, now we have all the parts to put into the Henderson-Hasselbalch equation. I'll go ahead and kind of erase this spot here, just to reclaim some board space. All of this as well. The pH is what we're looking for. It's going to equal the pKa, 7.041, plus the log of my base concentration, that's the 0.0535 molar, divided by the acid concentration, 0.158 molar. Let's figure out what that is. So 7.041 plus the base 10 log of 0.0535 divided by 0.158. I get a pH of 6.57. That is the pH of our buffer solution. So let's do one more practice problem because this is a pretty important type of topic that we need to practice a lot. I want to point one thing out. These are both molar concentrations. And both the base and the acid occupy the same volume because they're a part of the same solution. And so sometimes it is more convenient to not talk in terms of concentrations and instead talk in terms of moles. And so if we wanted to, we could rewrite the Henderson-Hasselbalch equation to just be pH is equal to pKa plus the log of the number of moles of A minus over the number of moles of HA. Okay, and that's actually the form that will be convenient for this next problem. So just keep that in mind. I'll actually change it up here so that we have that to reference. That would be n the number of moles of A minus over n the number of moles of HA. Okay, so H2PO4 minus has a pKa equal to 6.8. 6.80. And dihydrogen phosphate is actually a component of our blood that is largely responsible for regulating the pH of our blood. And blood has a pH of 7.4. Our blood is slightly alkaline. And so if we have a concentration of HPO4 2 minus in our blood equal to about 0.200 molar, then can we find the concentration of H2PO4 minus? Let's find H2PO4 minus. In order to maintain proper blood pH. Well, we're going to take our pH and our pKa and just plug them in here. The pH is 7.4. That's going to equal the dihydrogen phosphate pKa of 6.80 plus the log of our base concentration, 0.200 molar, over our acid concentration. Okay, now we can solve this by taking 7.4 and subtracting 6.8. That's going to be 0.60. I'll put an extra sig fig on there. So 0.60 is going to equal the log of 0.200 molar over H2PO4 minus. And we can get rid of that log by taking 10 raised to that power. So in other words, 0.200 molar over our H2PO4 minus concentration is going to equal 10 raised to the power of 0.6. We can just kind of swap these. We can take H2PO4 over here, and then we can take 10 raised to the power of 0.6 over there. And so we can say that H2PO4 minus concentration is going to equal 0.200 molar divided by 10 raised to the power of 0.6. Of course, we could have calculated any of those intermediate quantities, but I just wanted to do it in one go because it's not that complicated. 0.2 divided by 10 raised to the power of 0.6. And let's do first a quick little estimation. Blood has a pH that is more basic than the pKa value of dihydrogen phosphate. So we would expect to have a higher concentration of the conjugate base. Hopefully we'll get something less than 0.2, and we do. We get 0.050. So our, I'll just put it right here. Our H2PO4 concentration is 0.050 molar. Okay, now here's where the number of moles comes in, and I lied because that was actually most helpful using molar concentrations. But now we can answer questions about buffer capacity. How many grams of HCl could be added to 5 liters of blood? Actually, I'm going to make this simpler. Let's just say how many moles of strong acid can be added to 5 liters of blood before the buffer capacity is exceeded. Okay, so if I have 5 liters of blood, how many moles of HPO42- will that be? Well, 5 liters times 0.2 moles per liter is going to be N HPO42- is equal to 1.00 moles. That's just concentration times volume. And N, my amount of moles of H2PO4-, that is going to equal 0.05 molar times 5 liters, moles per liter. That's going to be 0.250 moles. And that ratio 1 over 0.25 is going to be the same as the ratio 2 over 0.2 over 0.05. And now at this point we can figure out the buffer capacity. I'm going to show you kind of the long, difficult way, and then I'm going to show you the easier way. Let's recall that the idea is that right now we have more base than acid. This is the base and here's the acid. Those aren't actually very accurate to scale, but if I add H+, then the amount of base is going to go down, and the amount of that conjugate acid is going to go up. And if I add OH-, then the amount of acid will go down even more, and the amount of base will go up. But the total number of moles stays constant. And so I can say here N total is the sum of the two. It's 1.250 moles. So if I want to know where the buffer capacity is broken, that's where this ratio gets out of sync such that it's a ratio of 10 to 1. And so let's just say that NB over NA, what'll be my total number let's say that's equal to 10, right? And that is going to equal when I have X number of moles of B and 1.250 minus X number of moles of A. This way I can figure out exactly how high does my B column need to be in order to represent that limit of buffer capacity where the number of moles of base over the number of moles of acid is equal to 10. Okay, so this 1.25 moles is the total, and so if I have X moles of conjugate base, then I'd have 1.25 minus X moles of conjugate acid, and so that means that, I'm running out of space here, but X is going to equal 12.5 minus 10x, and so 11x is equal to 12.5. And what is x? 12.5 divided by 11. And that's 1.14. 1.14. And if we wanted to go the other way, find it when NB over NA is 0.1, then we could just say that that would be when the amount of acid is 1.14 instead of the amount of base. And so now finally we're ready to ask the question, if I want to know how much acid I can add to this buffer, if I add acid, then that's going to convert my amount of base into amount of acid. I can add enough acid to change this number from 0.25 moles to 1.14 moles. So I can come here to my calculator and I can just say 1.14 minus 0.25. I can add 0.890 moles. So I can add my buffer capacity for 5 liters of blood, which is about how much blood we have, is 0.89 moles of acid before our buffer capacity is exceeded. And then if we wanted to look at the amount of base that we could add, well, base is going to convert our amount of acid into conjugate base, and so we just need to take that 1.14 and subtract the 1 mole, and that's just 0.14 moles OH minus. That's how many moles of H plus 5 liters of blood could be given before the buffer capacity is exceeded. That's how much OH minus. And you'll notice our blood is more strongly buffered against acid. That's because it had more of the conjugate base to do the buffering. Okay, so that's the hard way to do it. There is a cheat or easy way, and that's just to say, how much acid can I add? Well, I can add about 1 mole. Let me make sure that that's out of the way. I can add about 1 mole because I've got about 1 mole of base to react with. That's off by 10%. It's not a great estimate, but frankly that range of 1/10 or 10 for the ratio of base to acid, that was a bit of an arbitrary range anyway. So, you know, I can add less than 1 mole of acid. How much base can I add? I don't know, a little bit less than 0.25 moles. Here, that's a larger error than before, but you know, it's still in the right ballpark. And again, that range of 10 versus 1/10 was a bit arbitrary, and so some textbooks even present that as the true buffer capacity is just the amount of conjugate acid you have is the buffer capacity against bases. The amount of conjugate base you have is the buffer capacity against acids. And it's so much easier that it's decent as a rule of thumb. Okay, and that's it for 17.2.